Hi guys, Lauren Smith here. I got a H1 in Physics and Maths and I'll be walking you through 2019's higher level question 1. Today's experiment question is to determine the acceleration due to gravity with a ball and release mechanism. So, let's get started. Okay, so here's the first look at our question 1, the first experiment question on this 2019 paper. And it is an experiment to determine the acceleration due to gravity. Just be careful with these questions. There are 2 mandatory experiments on the Leaving Certificate Physics curriculum to determine the acceleration due to gravity. There's one that involves the pendulum and the one that involves the free fall timer. This question, we are looking at this free fall timer version. So read the question very carefully so that you don't mix up between the two. So we're given a table of data and we're naturally asked some questions that we're going to answer in this video. So let's get started. And the first question is draw a label diagram. I'm going to highlight the word labeled here because it's very important, of the apparatus used in this experiment. And here it is. I've drawn a nice big diagram, as you should in your exam solution booklet. Take up as much space as you need and make it as clear as possible. You don't have to be an artist in order to get full marks, that's for sure, clearly given my diagram. But I have labeled absolutely everything that I could to hone in the point that it is a label diagram. You will lose marks if it is not labeled. So what do you get the marks for? So you're going to get 3 marks for this ball and release mechanism, which is the electromagnet and the trap door. And that will get you 3 marks. Now this trap door, when closed so that the circuit is complete, it sets off the timer here, which labeling it and including it in your diagram will get you another 3 marks. And when this happens, the ball will start to fall, and after a brief period of time, it travels the distance s and hits the pressure plate. Indicating the pressure plate on your diagram will also get you another 3 marks. When the ball hits the pressure plate, the timer stops, and that's basically the run of this experiment. Now, what's very important to know, and which we're asked next, is between which points was the distance s measured? And the answer is, which will get you 3 marks, from the bottom of the ball to the top of the pressure plate. Now, big tip here, and I've included it here, a kind of a scaled down, not labelled version of the diagram we saw in the previous part of the question. Always indicate this distance on the diagram. It does help support your answer. It makes it very clear that you know what the distance s is. Because even if your wording is a little bit off, if you indicate it on the diagram, you're guaranteed to get some marks. As you can see, I've drawn s right in here. Now, like we've done in the previous parts of the question, we're asked to describe how the time t was measured. I briefly went through this. As mentioned earlier, the timer measures the time. Now, it's always handy when you're to describe how something was measured to include the apparatus in your description, because obviously the apparatus is key in physics experiments. So the timer does measure the time, but the timer starts when the ball is released. So mention your starting point and also mention your stopping point, which is when the ball hits the pressure plate, or equivalently, when it travels a distance s. This explanation will get you 3 marks. For the next part, where we have to draw a graph, I just want to look at page 50 of the Formula and Tables book for one of the equations to do with linear motion with constant acceleration, the formula which this whole experiment is based on. But also I want to look at page 18, because what we're going to need for this question is the equation of a line formula. Y is equal to mx plus c. And for this part of the question, we're asked to draw a suitable graph that can be used to determine the acceleration due to gravity g. Okay, so we're given a table of values here, and we have the distance s in centimeters and the time taken for the ball to travel this distance s in milliseconds. So we're going to have to change them into SI units, but we're going to have to change them a little bit more than that. What way do we need to change them, and where does this change come from? And why do we need to change them in this way? So as you can see down here in the second table I've drawn here, we keep S in meters, but we have to convert t into t squared in order to draw a suitable graph. Why is this? Well, this experiment calculates the acceleration due to gravity g from this formula. S is equal to ut plus a half at squared, which you will recognise from studying mechanics. The reason why we use this formula to calculate g is because the ball is undergoing constant acceleration, i.e. it's going at the acceleration due to gravity, so we can use this. So, since the initial velocity, or u, is equal to 0, and a is equal to g, or the acceleration is due to g, then this formula simplifies down to S is equal to half gt squared. And this is also in the form of an equation of a line. We know that the equation of a line can take the form y is equal to mx plus c, with m being the slope and c being the y-intercept. So we can say that here y can be read as s and our x values can be read as t squared, but our slope for the graph is equal to half times g, and the y-intercept is equal to 0. So therefore, if we find the slope of the best fit line of the graph, we can calculate g, and we know for a fact that this line goes through the origin because its y-intercept is 0. So first of all, we need to convert s and t into SI units so we can use them in the graph. So what we're going to do here is we have s in centimeters, so we're just going to divide each of the values of s by 100. So therefore we have s in meters, like this line here as follows. Okay, so that's s done. Now t is in milliseconds, so we're going to have to divide each of these t values in the table given to us by 1,000. And that's just a simple calculation. You can almost do it in your head. Now, a reason why I've drawn the second table is because even though s is in meters, and that's fine, we can leave it like that, like here, but we're going to have to convert t into t squared to calculate our x values for the graph. So let's just do an example of that. Taking out our calculator, our first t value per se is 0.250. We're going to square it, hit that equal sign, and we're just going to get 0.0625. The calculator gives it to 4 decimal places. However, the data we're given is going to be for 3 significant figures, or 3 decimal places, so we're just going to round this figure. Given our first t squared value, 0.063 seconds squared. Okay, and this can be just done by reading the table. You can see here that our t values given to us, there's about 3 figures there, so we're just going to give the same to 3 decimal places. And we're going to do this for the entirety of the table, and I'm just going to write down all of the values in this new table now. And there we have it. We have all our data values here. And by the way, we have this 2-table system here, which I would encourage you to do. I wouldn't encourage you to convert, say, for example, t, which is in milliseconds, just straight from milliseconds to seconds squared. I wouldn't recommend you to do that. I would break it down, convert it into SI units, then square it, because you are less likely to make mistakes if you take your time. No matter what level you are in physics, whether you're a H1 student or any other level, you can make mistakes in exam. It's called being human. So just take your time, and I would write both of these tables out so the examiner can see exactly what you're doing, and that even if you make a calculation error with the calculator, then the examiner can view it as such. Having all of the correct t squared values here will get you 3 marks. So take your time. It does matter that you get these right. So now that we have our y and x values for our graph, what will the graph look like? But the graph is going to look a little something like this, which I've drawn here, complete with a best fit line. And albeit it is not necessary, I would put a title on the graph. You'll be drawing on average 2 to 3 graphs in your exam, so you need to make it clear which one is which is why I've just put in at the side here. Normally you can do it at the top of the graph paper here. I've just run out of a little bit of room, but I've put my title in here. So the examiner knows, okay, this is the title. Okay, so this is the graph for question 1. Instead of the examiner having to read or guess which graph it is based on the axes. Now the axes, however, are very, very important. You are going to get 3 marks if you correctly label your axes. Now there's the 3 criteria for good axis labeling. So we need our variable, of course, like we have down here, we have t squared. You need the unit for that variable, which for t squared is s squared, but you're also going to have to scale your graph correctly and evenly. Like here on the x-axis, per every box, t squared moves along by 0.025. And for the displacement here, every box constitutes for 0.1. Now you get 3 marks here for all of these correctly labelled pink points which I've drawn, and you get 3 marks for the best fit line, which is in purple over here. Okay, so a couple of little points. Just remember the line must go through the origin, as the y-intercept c is equal to 0, as we saw earlier when we were looking at the equation of the line formula for the equation governing this whole experiment. Okay, so if some data points are not exactly on the line, that's okay, but try and angle the line so that you have equal amounts of points on equal spacings away from the line on either side of the line. As you can see here on my line, you have some points here, you have this point, say here, on directly intersecting the line. However, you have 1, 2, and I'm going to say 3, that's kind of midway-ish on the right hand side, and you have these 3 points over here on the left hand side of the line. So you have 3 on either side, so it kind of balances it out, and that's my whole point. Also, please, please, please never connect your points directly. That is not what the best fit line is about. You won't get a straight line, you'll get kind of a wiggly curve. So never do that. You will lose marks and you'll get no points for that graph. Okay, so that's the basis of drawing the graph. Now, all we have to do is calculate g. Okay, so before we determine g, we're going to need the slope formula, which you can find on page 18 of the Form in Tables book. Right, let's determine g. Well, we know from the previous question that the slope, or what we call m, is equal to a half g. So therefore, 2 times the slope is equal to g. So how are we going to find the slope? Well, you're going to find the slope using the slope formula, which is m is equal to y2 minus y1 over x2 minus x1, where x1, y1 and x2, y2 are 2 points which are going to be on the best fit line. So, which points are we going to use? Well, first of all, this will be my biggest tip ever. Always choose x1, y1 equal to the origin, or 0, 0. Because as you can see here, and especially from the formula y equals mx plus c, we saw that the y-intercept, or c, was equal to 0 in our previous question. And we know this because the best fit line must go through the origin here. So obviously, theoretically, the best fit line has to go through the origin. That's what the relationship between these points states. So therefore, it's going to be a very accurate point indeed. So I would use that one. And that goes for saying for any of the Leaving Cert Physics graphs, if your best fit line has to go through 0, always use this as a point. It's going to be very handy for you. Okay, so we need to find another point, or x2, y2. So what point are we going to use for that? Now, this point, whatever you choose it to be, it must be on the best fit line, as this best fit line best shows the relationship between your data points. Do not pick one of the data points given to you, even if it does intersect the line. The examiners really don't want that. They want you to pick one on your best fit line. because any point on the best fit line will best show the relationship between s and t squared, which is what we'll need to calculate the slope. So what I'm going to do is I'm going to pick my point, and I'm going to pick 0.45 and 0.09 as my x2, y2. And as you can see here, and I would encourage you to do this, I would circle or highlight the point that you're going to choose for your second point on your own graph so you can show the examiner, okay? That would just be my tip. Okay, so now that we have our points, let's substitute them into the formula. So we're just given 0.45 minus 0 over 0.09 minus 0. And as you can see here, even using the x1, y1 point as 0, 0 does make our calculation way easier. And I should mention that you get 3 marks for either mentioning the slope formula or substituting incorrectly your 2 data point values. But just getting 3 marks for just jotting down a formula, which you can copy from the formula and tables book, you don't even need to learn it off by heart, is very good. So that, again, solidifies the point that you should always, always, always put down any formula you use or think is relevant in physics in a physics question. Okay, so what do we do here? Let's just calculate what m is. Getting up our calculator, 0.45 over 0.09, it's the same as 0.45 minus 0 over 0.09 minus 0. The zeros don't really mean anything. It's just the same thing. So let's hit equals. And we just get a nice actually answer of 5, which is looking kind of good in the sense that we don't really need to round anything. And let's find the acceleration due to gravity. We know that g is equal to 2m. So that g is equal to 2 times 5, so that g is equal to 10 meters per second, okay? Now g in reality is roughly equal to 9.8 meters per second, so this is in and around an expected value. So we can say that this experiment is actually pretty accurate for an experiment done in the classroom, which is a great result. Where do you pick up your other marks? You pick up your other marks for calculating the slope as 5, and obviously for calculating the acceleration due to gravity, 3 marks each. And finally, we are asked to state an advantage of using a small, dense ball. And the answer that is accepted in the marking scheme is that an advantage of using this type of ball is that overall there is less air resistance. Stating this will get you 4 marks. Why would a small, dense ball inspire less air resistance? Well, it's a small ball because if the ball was too big, it would have a bigger surface area, and air resistance is quite dependent on the surface area of objects. Therefore, it would have a bigger effect on bigger objects. It's dense because if the ball were too light, it would be easier to be blown about. So you can really, really imagine how air resistance could affect the motion of this ball. And it's a ball rather than another object, like a spherical ball, because spheres have smaller surface area than most other 3D shapes. So it's very convenient to reduce the error air resistance has in this experiment because we assume that no air resistance takes place.